All right, so let's get this going here. 5.1 is our topic for today. And these are our fundamental trig identities. We're going to put the fun and fundamental. Do y'all know what fundamental means? It's like really, really important. The basics, the key things. Now, when I did notes on these last year, I made my students copy them all down. But I think to save us some time, we'll just refer back to what's on our sheet. So the ones that we're going to focus on today, I'll go ahead and I'm going to list the names of them, but you guys have that sheet out in front of you, right? And if you want to go back and copy them down onto your notes, if you're a completionist, then you feel free to go ahead and do that. The first one's going to be our reciprocal identities. Reciprocal just means 1 over something. And we've talked about these. I'm going to give let's give an example of one of them. The secant of theta is equal to the reciprocal of what? Secant goes with sine or secant goes with cosine? Cosine. Secant is equal to the reciprocal of cosine. Okay, this one is not on your sheet. See if you can complete this one. The tangent of theta is equal to 1 over. Ooh, tricky. This is not on your sheet, but can you figure this one out? What is tangent the reciprocal of? Cotangent. Hey, good for you. So I only included the 3 big ones on your sheet, but I need you to be able to go like tangent, sine, and cosine with these also. I don't have much to say about the reciprocal identities. We'll be talking about some of the other important ones here in a sec. Let's just go ahead and move on. We've got our quotient identities. And these are so important that we actually introduced them back in chapter 4, or at least one of them. When we were talking about the unit circle, we talked about how tangent, I'm going to go x instead of theta, tangent is equal to, if y'all remember what it is, sine over cosine. We didn't use cotangent that much back in chapter 4, not in this regard or in this way, in this context. But knowing that cotangent is the reciprocal of tangent, we should be able to write a fraction for cotangent also, right? What is the reciprocal of sine over cosine? Cosine over sine. Bless you. Not a whole lot to say about that one either. Well, that was way faster than 10 minutes. Nice. Okay. She did say less than 10 minutes, so I guess she was being accurate. Under promise and over deliver, right? Okay. So we're going to introduce something coming up here, and in order to do that, I want to talk really quickly about our unit circles. So if I could get you guys to sketch an XY axis for me real quick. And on that, I'm going to go ahead and do my best to draw a nice circle. Oh, it's going to turn out lumpy. It's in the spirit of a circle. And if this is the unit circle, then the radius would be equal to 1. which would make this point right here 1, 0, right? All right, and this is going to become really important with a lot of the stuff we're going to do in this unit. So I'm going to go ahead and draw myself a nice right triangle inside of this circle so that the hypotenuse is a radius. And let's call this angle here, this would be our reference angle. I'm calling it theta. So the radius, of course, would be 1. Do you remember how we relate trig to the coordinates of that point that's on the unit circle? The x related to one of our trig functions and the y related to that. What do you want? X is the cosine and y is the sine, or is it flipped?
Y is the sine.
Y is the sine and x is the cosine? Y sine? That's how you remember it? Y sine. Good question. Yeah, I remember alphabetical order. X comes before y, cosine comes before sine. But you're right, x is the cosine, y is the sine. So I'm going to redraw this triangle a little bit bigger off to this side here. This is going to be true for any points on our unit circle, that the x is the cosine and the y is the sine. So same triangle, just blowing up a little bit. This is 1. This is cosine, and this is sine, right? The x coordinate, the horizontal portion of it would be the cosine, the y coordinate, vertical portion would be sine. So we're using this a ton in geometry right now. If I ask my students to write me an equation in geometry that relates to 3 sides of a right triangle, what type of equation do they write? What's that super famous equation that everybody remembers from high school? A squared plus b squared equals c squared. Some people call that the whose theorem? Pythagorean theorem. And what will go inside of each of these blanks? So it would be cosine and sine and 1. And that's how we come about the Pythagorean identity, the first Pythagorean identity. So if you look at your sheet, your trigonometric identities, they've got a slightly different order. They've got sine squared first. Doesn't really matter what order we put it in though. Cosine squared theta plus sine squared theta is equal to 1. Or usually we put sine first. Sine squared plus cosine squared is equal to 1. This notation is a little bit different. It takes people some getting used to. When you see a cosine and the cosine is squared, what that indicates is that you've really got a parenthesis around the whole thing, then it's squared. Now this gets a little confusing to a lot of people because then they're like, well, what about inverses? What does it mean when a -1 is here? Does a -1 mean that there's a -1 outside of the whole thing? And the answer is no, the -1 means it's an inverse. So it's a little bit different. So, but when you see a 2 or a 3, it means we're actually squaring the whole thing, the cosine with the theta inside of it. Okay. This is going to become super important. You guys are going to use this like almost always. Like every single homework assignment for this entire unit, you'll be using this one. And you're going to get really good at watching for those sine squared plus cosine squared. So those are called our Pythagorean identities. And I want to show you how to memorize the other 2. You want to know sine squared plus cosine squared equals 1. The key one to know is that sine squared theta plus cosine squared theta equals 1. You're going to see that again and again and again and again and again. With us? with us? Now there's two more. Do you see the other two on your sheet there? On your super fun sheet of fun? Two more Pythagoreans. There's also tangent squared plus 1 equals secant squared, and there's 1 plus cotangent squared equals cosecant squared. Do you see those other two that are listed there? I personally only have this one memorized. I don't usually memorize these other two, although this might be the year that I actually get around to doing that. I'll show you my trick for the other two. So I'm going to write this down underneath it. Sine squared plus cosine squared equals 1. Check this out. This is a nice little trick. Algebra says we can do the same thing to both sides of the equation as long as we do the same thing, right? And it's, when that comes to multiplication and division, it means you have to multiply every single term or divide every single term by the same thing. I am going to choose to divide every one of these terms by cosine squared. And look and see what we get. What is sine squared over cosine squared? What's sine over cosine again? Sine over cosine is tangent. So sine squared over cosine squared is tangent squared, right? Oops, that's a plus, not an equals. What's cosine squared over cosine squared? That's 1. What's 1 over cosine squared? That's the reciprocal of cosine squared. That is secant squared. And there's the second one, tangent squared plus 1 equals secant squared. So as long as I start from this, I can get to the second one. You can actually do the third one doing the same thing. So start with sine squared plus cosine squared equals 1. So when I'm doing these, I usually just abbreviate them. What am I going to divide by this time instead of dividing by cosine squared? Let's divide by sine squared. What's sine squared over sine squared? That's 1. What's cosine squared over sine squared? Cosine over sine. Now that's not tangent, it's the backwards of tangent. So that's cotangent. And the reciprocal of sine squared? Cosecant squared. So this is the main one. This one comes from the fact that sine and cosine give the coordinates of the point along the unit circle. You make yourself a right triangle and use Pythagorean theorem. That's where this comes from. These other two come from taking this one and dividing everything either by sine squared or cosine squared. I'll be honest with you, my life would probably be a little easier if I just memorized these two things separately. Okay, but you're going to see this come up a ton. All right. Cofunction. Let's talk about cofunctions. Anybody have any questions so far? I bet a lot of you are thinking like, how are we actually going to use this stuff? Anybody thinking that right now? No? Okay. Cool. I don't have much to say about cofunctions. We don't end up using these as much once we get out of this section, but they do come up from time to time. So when I say cofunctions, I'm talking about sine and cosine are cofunctions, right? Because there's sine and then there's the other one that's the same thing except it's got co in front of it. Tangent and cotangent are cofunctions. Secant and cosecant are cofunctions. And it turns out that if I take any function and instead of doing the sine of x, if I do the sine of pi over 2 minus x, I'm going to get the cofunction of just x. So this is sine, so this is going to be the cosine of just x. If we were talking in geometry about pi over 2 minus x, anybody know a good vocabulary word for that's 90 degrees minus x? So if I said 20 degrees, then 90 minus 20 would be 70, right? 20 degrees and 70 degrees are what kind of angles? What's the word for two angles that add up to 90? Add up to 90. Wow, that's a really nice shirt you're wearing today. I like your new hairdo. You're a very nice person. Complimentary. That's not spelled the same way as the compliments that I was just saying, but complementary angles. So this kind of comes from complementary angles. And I don't know if you would have learned this in geometry or not, but well, it comes from, I'll show you where it comes from. They probably didn't show you this in geometry. Right triangle trig, right? Bear with me here a second. Here's theta. And let's say I've got A, B, and C, right? What's the difference between theta and x? How are they related? Can we agree that they add up to 90? Yeah. So theta is 90 minus x and x is 90 minus theta. Agreed? All right. So if I took the sine of theta, that would be equal to of theta. That would be a over c. Agreed? What if I took the cofunction, the cosine of, instead of theta, x? What would that be? It would also be a over c, wouldn't it? So it turns out that the sine of an angle is equal to the cofunction of its complementary angle, the other angle in the thing. That's where it comes from. But it actually works with angles that are not between 0 and 90 also. The thing I need you to remember is I just need you to what's going to happen is you're going to end up seeing sine of pi over 2 minus something appear in a problem. And I just need you to look at that and say, you know what, I think it would be much simpler to call that cosine of x instead. We'll see how this comes up in just a second. We've got an example that has cofunctions in it. So, all right, let's talk even and odds, and then we'll go on to some actual example here. I need you guys to remember about even and odds. We introduced this way back in chapter 1. You saw it in algebra 2 also? Good. It's gonna affect your life in pre-calc as well. So even and odd. Let's just review all the way back to chapter 1. If something is odd, then if I take f of the opposite of x, that's where we always start when we're dealing with this. What am I going to get if it's odd? So I've got a function. My function is f of x. If I plug in negative x and I get back the opposite of f of x, that means it's odd. Which means it's symmetric about the origin. If something is even and I take f of the opposite of x, what am I going to get back? We'll get f of x, which means symmetric about the y-axis. All right, we're going to draw a little picture here and try and apply this to our unit circle. So go ahead and draw that XY axis in your unit circle again for me. That's a pretty decent circle. One of my better potatoes. Don't draw a triangle on it just yet, though. Not just yet. Now, when we're dealing with trig functions, the x, the input represents what? What do we always put into a trig function? What always goes inside the parenthesis when you're setting up a trig equation? Is it a side or is it an angle? The angle always goes into a trig function, right? So the x in this case is going to be our angle. So I'm going to draw myself a line going up like this. And I'm going to say that this is my angle x. X degrees, x radians, it doesn't really matter. That's the angle. And that's going to create a point up here, right? And let's go ahead and label the coordinates of that point. The x coordinate of this point, relate that to x in a trig function. The x coordinate of this point is going to be cosine. So this will be the cosine of x. And the y coordinate will be the sine of x. You with me so far? All right. Now I'm going to draw another angle and I'm going to try and make it the exact same angle. So I'm trying to be symmetric here, except it's going to go negative. This is negative x instead of positive x. So this point then would be the cosine of negative x and the sine of negative x. Agreed? All right, now I need you to use your brains. And I want you to look at these 2 points and I want you to think about their x coordinates. If all of this is symmetrical, what is going to be true about the x coordinates of these 2 points? They will be exactly the same. The x coordinates. The x coordinates would be the same. Same x coordinates here and here. Those 2 points would have the same x coordinate, correct? Which means that the cosine of x must be equal to the cosine of negative x. Actually, let's write it the other way around. The cosine of negative x is equal to the cosine of x. Is cosine odd or even? The cosine of negative x is the same as the cosine of x. It is even. It's even. That's the definition of an even function, isn't it? If we plug in a negative x, we get the same thing as if we plugged in just a regular x. That's the definition of an even function. So cosine is even. Cosine is an even function. Think back on our 2 points here. What's the relationship between the y coordinates of these 2 points? Are they the same? No, they're opposites, right? So they're opposite y coordinates. So the sine of negative x is not the same as the original sine of x, is it? It's the opposite. It's the negative of sine of x, which makes it odd. That's the definition of odd. If I put a negative x in and I get the opposite of the original, that's an odd function. So that's where these ones come from. So when you're looking at your sheet there, you've got your odd and even functions. And it turns out that sine is odd and cosine is even. And so that's where this comes from. The sine of the negative angle is equal to the negative of the sine of the angle, and the cosine of the negative angle is equal to the cosine of the original angle. It turns out the tangent is odd as well. And then the reciprocal functions all follow along with their original functions. So since sine is odd, then cosecant is also odd. Since cosine is even, then secant is also even. Why does this matter? That's a great question. So right now, all you've gotten is like, okay, here's a whole bunch of things, right? So there's two things we're going to do with this. One, we're going to simplify. That's going to be the majority of your homework, and we're about to start examples on that, right? So thank you for your patience. I know that right now you're just like, I don't know exactly why I'm soaking all this in, but I'm doing my best here. Um, um, and then eventually we're going to get into trigonometric proofs. We're going to use these as ways to move from one expression to another expression. So right now, all I'm doing is I'm introducing this first whole big old set of identities that you're eventually going to memorize, right? And just trying to show you why they work. I'm also trying to give you a couple hints so you don't have to memorize every single one. Like, I don't know all 6 of these. All I know is that sine and tangent are odd and cosine is even. And that's enough for me to put these together. Because I know what odd and even are, right? I know that odd means that if I put in a negative input, I get the same thing as the original with a negative out in front. I know that even it means if I put in a negative input, I get the original thing without a negative in front. Now we'll actually start on some examples. Does anybody have any questions other than why are we learning all this stuff? Which is a wonderful question. Thanks for asking that. All right, let's do this. So now we're going to do some actual examples, and I've got 5 of them here. And we'll just work through these together. And I'm going to tell you that these are not, what we're getting into here are not super straightforward problems. This is not a step 1, step 2, step 3 kind of thing. And there will be multiple correct answers for some of these. So for all of these examples, our instructions are going to be simplify. So in the context of today, your question was, why are we learning all this stuff? Well, we're learning all this stuff so that when we get to calculus, we won't run across some weird trigonometric expression that's got a bunch of sines and secants and cosines in it. Can we use these identities to simplify it, turn it into something that's going to be much easier for us to deal with? All right, so we'll start with a pretty basic one. We're going to look at the expression cotangent of x times the sine of x. Now you can format your work however you'd like to for these problems. A lot of people like to kind of move them across the page and go step by step across the page. I am going to format my work in the way that I'm going to ask you to do once I teach you how to do proofs. So if you kind of get in the habit of doing it the way I'm going to show you right now, that's going to lead you direct. It's going to get you into a habit that you're not going to have to think about when you get to proofs. Your choice. But what I'm going to do is I'm going to say equals, and then I'm going to put my first step here, and every subsequent step I'm going to put underneath that. So my steps are going to look like equals, and then equals, and then equals, until I get it to the point that I can't simplify it anymore. All right, so we want to simplify this. Sometimes we need to make it more complicated in order to simplify it. Can we think of another way to write cotangent, or think of another way to write sine that might make this a little bit simpler? Cotangent is cosine over sine, correct? Okay, so we're going to write, I'm just going to rewrite cotangent as cosine x over sine x. And we'll leave sine alone. Okay, I'm just going to do a little outlining here. I wouldn't normally do this in my work, but this is becoming this, right? And what's going to happen when we multiply cosine x over sine x by sine x? These signs are going to cancel, aren't they? Cosine x. And I'd say that's as simple as we're going to get. So that's my answer. So we started with 2 trig functions and we ended up with a single one. That's the gist of what we're going to be doing. Okay, so mostly, for the most part, we're trying to write them as a single trig function. Although I'll tell you, sometimes they come out to be numerical answers. So let's do another one. You guys are doing great so far. All right, we'll start out a little bit more complicated this time. Let's start out with cosecant x times sine pi over 2 minus x equals. And I'm going to ask that when you're doing these problems that you only apply one type of identity at a time. So when I see this, this is supposed to be a pi, sorry. When I see this, I see two types of identity. This is the one that my brain cues into first. Pi over 2 minus x. I remember that being on my sheet. Do you guys remember that? Yeah, those are our co-function ones, right? So I would probably change this one first, although some of you might be looking at this cosecant and thinking about turning it into what? 1 over sine, which we might be able to, we'll probably end up using that in a second, but let's go ahead. I'm going to focus just on this. So I'm leaving my cosecant alone. And I'm going to turn sine of pi over 2 minus x, this is cofunction, into the cosine of x. And again, I probably would not do this in an actual homework assignment, but I'm just doing this to kind of usually a good sign. 1 second, please. Okay, so boom, 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 there we go. Okay, so this looks like we could probably still simplify it a little bit more. I'm thinking about maybe leaving the cosine alone now and changing this into 1 over sine x. And leaving the cosine alone. All right, so this time I took this guy, turned it into this, left the cosine alone, and then, yeah, we could put those together into a fraction. That's going to happen a lot. You're going to see two fractions or two things being multiplied together. It's, a lot of times you're going to end up putting them together into a fraction. We got cosine x over sine x, and that's equal to, oh, that's familiar. That's not tangent. Tangent would be the other way around. That's cotangent x, and I would say that's good to go. Okay. So are we starting to get an idea of why we're doing these? Because you're going to get to calc and you're going to end up with something like this inside of an integral, which, you know, integrals are something you don't know much about right now, but it's something that's kind of messy to deal with. And especially when you have multiple things multiplying together and something on the inside of a sign like this, ooh, I don't want to deal with that. If there's something I can do to simplify this, it's going to make my life easier. So that's the main purpose of what we're doing here. So we had to use three identities, I guess. Cosine over sine was cotangent. So we used our co-function identity. We used a reciprocal identity to get to here. And then we used one of our quotient identities to get from here to here. Are we feeling confident with number 2 there? Ready to try a little different, more difficult one? We can't wait. All right. Make your attitude. We're going to go cosecant squared minus 1 over cosine squared. So a lot of these types of problems, you're going to find yourself getting better and better at it the more you're familiar with the things on the sheet. Yes, I'm not going to, you are going to have the sheet in front of you when you're doing your test. But you're going to be better off if you can look at this and recognize, ooh, that looks like one of my Pythagorean identities. You're going to get to the point where you see cosecant squared minus 1 and say, ooh, that's one of my Pythagorean identities. Look at your Pythagorean identities and see if you can figure out which one it is. Which one has cosecant squared and 1 in it? The third one has cosecant squared and 1. Ah, but it's not cosecant squared minus 1, is it? Cosecant is equal to 1 plus cotangent squared. Oh man. So we could subtract 1 from both sides and then it is the same, okay? Now I prefer not to do it that way because it tends to make things more confusing. So here's how I would tackle this, okay? I'm gonna leave the -1 here. And I'm gonna leave the cosine squared here. My identity says that cosecant squared is equal to what? Cotangent, 1 plus cotangent, right? Oops, I left out my x in my original problem. There should be an x. So I'm replacing something with something that it's equal to on my identity sheet. And then in my second step, I'm going to lose those 1s. So that's oh my goodness. Cotangent. I invented a new trig function. That's cotangent x squared over cosine squared x. How many of you would have just jumped from here down to here? All right, I'm okay with that. This is more readable to me. But for these types of problems, and in terms of when we do get around to doing proofs, if you were to jump straight from here to here, I'm okay with that. So my cosecant squared ended up becoming this 1 plus cotangent squared x. Okay, now I'm not a big fan of that. That looks like we could probably go a little bit further. I'm also not a huge fan of, well, what are you guys thinking about doing next? You want to turn cotangent into something? We could do that. We're going to have fractions inside of fractions. Is that good or is that bad? Are you okay with that? You all right with that? So I'm going to split this one up and go 2 different directions. You can just see which one you prefer. Direction 1, I'm going to go ahead and go with what you just said. Now, when you start getting fractions inside of fractions, then over exaggerate your fraction bars so you know which one's the main fraction and which one's the fraction that's inside of it. So cotangent is cosine over sine, right? You see how I really exaggerated the main fraction bar? Make sure you do that or you're going to lose track of like what's in your numerator and what's your denominator. All right, where do we go from here? Yeesh. Well, I'm going to want to see a step in between there. You're right, it will be. So you could turn this into so you could turn this into cosine squared over sine squared times 1 over cosine squared. You could do it that way. That's how I'm going to do it over here. I'll show you what I would probably do from here is I would keep this. I would go, this is cosine squared over sine squared x. And we still have a cosine squared x. I'm going to multiply by a fancy version of 1 times sine squared x on top and bottom. So now these are going to cancel here. So I have cosine squared over cosine squared sine squared. And the cosine squareds are going to cancel. So I have 1 over sine squared x, and I ran out of room. I need to see steps though. Like this is one of those things like in geometric proof where you don't just jump from one step to another. So I don't want you going straight from here to 1 over sine squared. I need to see at least 1 step in between to show me how you're getting that. Now, here's a more straightforward way that I would deal with it. Rather than go to fractions inside of fractions, I would go from here. I would leave this alone, but I would call it cotangent squared x times 1 over cosine squared x. That's how I would have tackled this. Instead of dividing it, we're multiplying it by its reciprocal. That's what you just suggested a moment ago, Franklin, right? And then from here, then I would change the cotangent to cosine squared over sine squared. And leave that 1 over cosine squared alone. And then I would cancel the cosine squared to get 1 over sine squared. And then I would go, that's cosecant squared. So that'd be my preferred way of doing it. Either way, we're coming out with cosecant squared with this one, though. All right, we got a couple more on us. Let's do 2 more. Any questions? All right, let's do 2 more. Example of the 4th. The sine of, do you guys need to step out for a second and collect yourselves? It's getting a little disruptive. Or maybe move to further separated seats. Do what you need to do, okay? Thank you. Did we do this one already? We did something like it, didn't we? Kind of similar. All right, so you're going to find that when you start getting good at this, you'll look at the original problem and you'll start thinking, what kind of identities do I see here? What do you see with this sine negative x? What type of identity are we looking at there? That's an even odd one. So we could deal with that first, or what are you seeing with that secant pi over 2 minus x? That's a cofunction run, right? So we're only going to do one type of identity in each step. Now, if you had 2 odd evens, if you had 2 odd even things going on in the same problem, you wanted to take care of both of those in the same step, I'm okay with that. But these are not the same types of identities, so we're going to do one at a time. So which one do you want to do first? Why don't you move over here? Thank you. Which one should we do first, the odd even or the cofunction? Odd even? All right, I heard odd even first. So I'm going to leave the secant alone. The sine of negative x is, since sine is odd, that's going to equal to the opposite of the sine of x. And I'm leaving secant alone. And then why don't we go ahead and take care, let's leave the sine alone. Secant is going to become, what does that turn into? This is a cofunction one. What's the cofunction of secant? Cosecant. And that would just be x, right? When we go from pi over 2 minus x, we just turn it into the cofunction of whatever that is, and it's just an x now. Where shall we go from here? We could use a reciprocal function on this cosecant, turn it into 1 over sine. So we'll leave the negative sine x alone, turning cosecant into 1 over sine x. Ooh, those are going to cancel. -1 for the win. All right, time for my favorite one. All right, this next one has like, oh, there's probably 16 different routes to take for this one. So, and none of them are super friendly. All of them take several steps. So, all right, you're gonna love it though. we got the sine x times the quantity tan x plus cotan x. And I got notes in front of me with one way, but I want to see what you guys come up with on this one. So the question is, do we want to deal with this stuff inside? The question in my mind is, do we want to deal with the stuff inside the parentheses first and leave the sign alone for a while? Or do we want to go ahead and distribute the sign into the parentheses and deal with it that way? What do you guys, where are you leaning? Do you leave it inside or distribute and kill the parentheses? Leave it inside. I know a couple of you are at least saying distribute. Well, it's entirely up to you. Should we vote? I'm seeing more people, I'm hearing more people say leave the stuff inside. So I'm going to go that way. For the couple of you who said go ahead and distribute, I challenge you to go ahead and try that and see if you can kind of come up with a similar answer. Okay, so if we're going to leave it inside, if we're going to leave that sign alone, then what can we do with that tangent and that cotangent? What are you thinking? We do quotient with both of them. We can do that right in the same step since it's the same rule for both, right? So we'll turn tangent into sine over cosine. And we'll turn cotangent into cosine over sine. All right. Now I'm going to show you something that's going to become super important when we end up doing proofs, and you'll run across this a couple times in our homework for tonight too. One of the big strategies that I'm going to show you when we come together again on Wednesday is if you ever end up with a situation where you have two fractions that are being added or subtracted, it is often a good strategy to try and combine them into a single fraction with a common denominator. Okay, so that's what I'm going to do in this next step. There are other ways to accomplish this, but I've just done enough of these that I know that if I can combine these together into a single fraction with a common denominator, that's probably going to get me somewhere where I need to go. So I'm going to leave that as sine x, and I'm actually going to leave the sine x over cosine x. I'm going to leave some space after it, and I'll do a cosine x over sine x, and I'll leave some space after that too. And I'm going to multiply by some magic ones here. You all right? We'll multiply by some magic ones. If I'm trying to get a common denominator here, I need both the denominators to have, what's our common denominator going to end up being? Well, it's going to have a sine in it, but it's also going to have a cosine in it. So it's going to have sine cosine in it, right? So this denominator is missing a sign. It's going to have a sign in it eventually. So I'm going to multiply this by sine over sine. It's just a 1. It's a fancy 1. That's going to get me a denominator in this fraction of cosine sine. Agreed? And what am I going to multiply by? What's my fancy 1 here? Cosine over cosine. That should get me the same denominator in both fractions. Agreed? So I should be able to then write this as sine x times, this is all going to be one big old fraction now. And because the denominator is now matched, they both have a sine x and a cosine x. And on the top of that, I'm going to be adding some stuff together. And what am I going to be adding together? Ooh, that's sine squared x. Plus cosine squared x. Ooh, you're going to get really excited whenever that comes up in one of your problems. Sine squared plus cosine squared. Yes! What is that equal to? That is equal to 1. Sine squared plus cosine squared. That's our Pythagorean. That's that super special Pythagorean theorem. Awesome. Okay, so this sine x stays. And this is just 1 on the top now. Sine x, cosine x on the bottom. Oh, I like where this is going now. That just simplified a lot. Now what? We could distribute. I'm thinking we could cancel this. We're multiplying and dividing both by sine x. So let's just cancel them. That's 1 over cosine x. And then boom, there we go. That's secant. Did anybody try doing the distribution first? So when you did that, you probably ended up with just a messier version of this.
I felt like it was less.
Oh, really? Can I see it? Let's see how yours went. Can I put it up on the screen?
Yeah.
All right, let's have a look at this. I'll let you guys decide what you think. So we distributed here. Now these parentheses you're using here aren't technically necessary, but that's all right. And then you're going into your quotients here. And then you're able to cancel the signs here. So you ended up with sine squared plus cosine squared. No.
Yeah. Oh, sine x. Oh, sine squared.
You ended up with sine. So I would probably insert one more step in between here, just to make it a little bit clearer. What you ended up with was sine squared x over cosine x plus cosine x, right? And then it looks like you multiplied by a fancy, you've multiplied this one by a cosine over cosine. And then that got you to here, which got you a common denominator. So you were able to put those together with just a cosine on the bottom. You had 1 over cosine. Yeah, that worked out. Pretty similar number of steps. Cool. All right, that's all the examples I got for you today, but I wanted to give you some time to get started on the assignment. This is the type of thing, if you've got a homework study group, make sure you're working together on these problems, because especially at first, the more you can work together, the more you can talk things out, bounce ideas off of each other. This way isn't working out very well for me. What did you try? That kind of stuff. You're going to find that this goes a little bit easier. The big thing that I need you guys focusing on is, as you're working on these, make sure that as you're working on them, that you're doing whatever you can to try and internalize these identities. Remember, your goal is going to be to memorize them by, I'm going to just say probably Tuesday of next week is when we're going to have our first quiz over this stuff. So if you could set a goal for yourself while you're working tonight to make sure you have, one of your Pythagorean and maybe your cofunctions, and then next homework work on making sure you know odd even and some more of your Pythagoreans. I don't know, however you want to do it. Start getting after that. Questions? Yeah, I think we got time for the tests.